microservices and model executions in real time. Quite simply, we call it quantum real time in Capital One. This is a homegrown project. Also, for the rest of the slides, I'm going to be referring it as quantum real time. Do note that this is not quantum computing. We wanted to sound like halfway cool, so we just took like part of the name. Basically, quantum real time is what it provides is like it provides out-of-the-box capabilities for real-time microservices and model executions at scale. Some of the other goals that we focused on is the fact that we wanted to provide like a simpler interface to develop and deploy real-time applications. A little bit about myself. I'm Srikar. I'm a software engineer at Capital One. Currently, I'm the tech lead of a couple of teams, one of which is developing quantum real-time. The other is a model-heavy use case, which also uses quantum real-time. So I'm kind of like the customer of myself. I'm passionate about distributed systems and big data and real-time applications. I've been with Capital One for a couple of years now.
I'm Erin Kavanaugh. I work on a use case of this framework. So both use it to run applications and models in real time, but also contribute to the framework. Before that, I was working on internal marketing tools at Capital One and have worked on some developer tooling as well. OK, so we're going to kind of give you an overview of why we built this and what it is before we dive into the architecture. So when we were thinking about what it was that we needed to do, we had several use cases across the company where we needed to run models in real time. And we wanted to focus on what was the common issues between them and how could we solve for it in a way that was reusable. So the first thing we thought about was obviously whatever we needed to build had to be focused on performance first. We needed to get results back very quickly. Scalability needed to be thought about early on. As we bring in more teams, we need them to know that we can scale to their needs and their users. The next thing was configuration driven. So we wanted it to be really simple for business teams to get started with the business logic and make it really easy for them to explain exactly what they need to do in a way that's easy to read, easy to reason about, and reusable across teams. So not everyone is having to redo the same code. The next thing is about the model consumption. We wanted our model developers to use the tools that they wanted to use. So whatever our framework needed to do, it needed to make sure that models wouldn't need to be recoded and we could do it in a language agnostic way. And lastly, we wanted to think about fault tolerance early on and ensure that we had logging tools in place so that they wouldn't have to contribute or to configure all of this upfront.
So as you may have observed by now, we're doing a little bit of real-time context switching here, slide by slide. So why did we build this? There was a recent shift within Capital One a few years ago. We wanted to be on cloud. We want to be developing all the real-time applications in terms of microservices, be really fast and scalable. For all of this, there was a very concrete need from use case teams that they want to have that capability for microservices and also be able to execute models in real time. So this brought up a concrete question. There are multiple teams doing this. What is an easy way of like enabling and making it easy for all of them? So that's where we came in. We tried to solve for this problem. And one of the things that we immediately identified is that every use case requirement is unique. Every data science need is unique. They're all solving for different problems, and for a company as big as Capital One, standardization is a very tough problem to solve for. And so instead of solving for that, what we decided to do was go the other way around. How about just relaxing everything so that we can facilitate all of those requirements and like keep things flexible as such. And this also brings in the question of like, great, we created a framework, but for all the people who are trying to use it, it has to be simple enough. They would want to like just take it, plug it in, start using it really fast. The time to delivery of any product should be really, really fast. So we also started approaching the problem likewise. Right.
So when we were thinking about this, we knew we had two main users. The first was the data scientists. So in the past, the data scientists would write their models in Python or R or whatever language they chose. And those models would need to be recoded into whatever application they were getting deployed on. So sometimes that was Java or Scala or whatever that was. And in that process, they couldn't use important libraries that they wanted to use. And the back and forth time between the data scientists and the engineers as they did that recoding could be error prone and involved a lot of interactions there. So when we thought about that, we wanted to ensure that the data scientists were able to use the tools that they wanted to do the training, the deploying, and the building. The second team, or the second user that we thought about was the engineers. So we wanted engineers to be able to really quickly start up a new application. And we wanted to put the deployment pipelines in place so they could iterate really quickly and make improvements. And so when we thought about this working model, we wanted to ensure that we would be able to provide collaboration and flexibility between the two of them by creating a really loosely coupled system. Both of them are able to work to focus on the things that they're really good at, and the working model between the two works really well.
All right. Coming back to technology choices, we have a problem to solve. We know what we wanted to solve. And now the bigger question is how do we want to solve it? We did evaluate a bunch of technologies to figure out what best fits for this particular problem. Along the way, we ended up with a few choices. Scala, we use Scala pretty extensively within the framework, primarily because it allows for functional programming, and it also gives that flexibility of object-oriented programming wherever it is required to. And most importantly, it integrates really well with Java libraries, so we don't have to reinvent the whole wheel if we wanted to use like any community-developed support. One of the important components of this entire framework is the utilization of Akka. Akka is a distributed messaging framework, which provides like an excellent out-of-the-box concurrency models using actor supports. So I'll explain in the further slides how we end up like using Akka actor system, which really helps us in the solution. Finally, Docker. We want to enable this particular framework for easily shippable content. So Docker enables that lightweight and easily shippable containers.
So we're going to walk through the framework, starting off with a really high-level overview of what it does, and then kind of getting closer down to the details. So somewhat obviously, what Quantum Realtime does is it starts up a real-time application. There are two main interfaces that we're running currently. One is a RESTful API microservice, or you can run it off of an event stream. You can run both of those interfaces at the same time if you have a workflow that needs to be run in multiple contexts. So that provides a lot of flexibility. The micro orchestration is kind of core to what the framework does. So that's the Akka that Srikar mentioned, and that connects the services to the business logic. We maintain a shared library of plugins, and each plugin is a component of business logic that can be either shared across teams or customized to a team's needs. And the feature library are the rules and policies that the application developers are creating. So at a high level, this is kind of the major pieces that you'll see throughout the rest of the slides.
We did speak about like how the framework provides like an out-of-the-box application interface. Once we start drilling down further, the primary goal was to provide those business functionalities, which are pretty much language agnostic and feasible to be plugged in by any user need. So let's dive into those plugins. Plugins primarily constitute of the models or feature execution requirements, or any business logic as such. So the way we approach this problem is these plugins could be written in Java or Scala or Python, and we needed a way to easily plug them in. Aside from that, there are always like external data sources that we'd like to talk to in order to procure the data and like process them further in order to enable the business logic for further processing. And so this is the framework is pretty well built in a way to communicate with the rest of the stuff too. On top of everything, for any application as such, logging at the end of the day is bottom line important. Whether you'd like to debug, whether you want to like understand how the flow works, or you would want to even like support monitoring requirements, logging at the end of the day is like a solid thing. And we would want to reduce the burden on application developers as such by providing a whole lot of out-of-the-box logging too.
Cool. So this gets in a little deeper to what a quantum real-time application looks like. So it's made of two main configuration files. One is the JSON workflow configuration, and the other one is the application configuration. The JSON workflow configuration lists out all the routes, all the workflows, and all the communication between them. So that includes the DAG, which you'll see here. So all of the business logic, which is what we call plugins, are those red circles there. And quantum real-time is handling the communication between them with the executors. So those are the Akka actors that provide the seamless communication between all those plugins. The application configuration file is where we store constants, environment variables, and those kind of things. So we can write really reusable and generic business logic plugins that can be shared across teams.
All right, here comes the meatier part of quantum real-time. This particular slide actually shows one of the fundamental blocks of it. And by now, I'm assuming that most of you actually know what a DAG is. Or in general, DAG is literally directed acyclic graph. So remembering about like how we wanted to approach this use case requirement, the way we reimagined the whole stuff is that for any given requirement or a use case set of requirements, they can be broken down into simple DAGs, where the graph nodes can represent the business functionality, and the edges that are connecting them are simply the connectors to those logical subdivisions of the work. Now, the only thing that's differing between a use case to a use case is that the core functionality of that business plugin is changing. But those connections which formulate those edges are basically the same. They can just be switched around. So in a way, we just wanted to create that orchestration layer which just abstracts away the burden for the application developer to keep on repeating the same orchestration job like over and over again among the use cases. Let's walk through this particular diagram. Those red and blue circles, as you see, form the business functionality, where the red part of it is actually the core business logic for individual components. And then the way we made use of Akka is that we're wrapping each one of those business logics around by an actor. So they're literally getting encapsulated by actors. So at the end of the day, they don't really have, within the system, they don't really have to know what is the other plugin that is actually existing within that application. All they have to know is that the system comprises of a bunch of actors, and they know how to send and receive messages because it's a very standard interface. And we also spoke of like how these plugins can be language agnostic. They can be written in Scala or even Java. We also have a way of like integrating Python data science models directly. Some other aspects of this is that if there are capabilities that can be run in parallel, if they don't have to really wait on each other, they can literally be configured to do the same. Few things that data scientists usually run into is that, say, you're running a model in production, you have a model version 1.0, and that's actually affecting your customer. Now, you would also want to test out like some other versions of the same model to figure out how are the other model versions performing. So in a way, you would want to do shadow scoring without affecting the end customer. There are certain patterns that we came up with where we can do those tasks asynchronously. I'll talk a little bit more about those asynchronous tasks and how we came about, but one of the important things over here that enables that functionality is that we also have like stream capabilities where there are certain generic plugins which are available within quantum real-time, which would allow one to publish data or events to a certain set of streams, like Kafka streams. And the rest of the flow just follows accordingly, where you can combine multiple models, you can just do further processing on them or insert into sinks as required. Let's look at the higher level architecture. Now, this diagram may look messy because application development in the end is an actual messy process. Let's walk through from right to left, where in the previous slide we looked at a workflow, which is a simple DAG. Now, that particular DAG or a business functionality in general is fitting all the way on the workflow processing layer, which is to the right side of it. That's all. Just about everything else are the common set of things that are required for any application as such. As you can see, we have like 3 layers in this. One is a workflow processing layer where the business functionality actually sits. And then there is an orchestration layer, which is also provided out of the box, which enables processing of those workflows, which also like receives the required requests and then knows where to forward those requests in order to process them. And then we created a logical separation for the services themselves so that any number of services added, currently there are a couple of them, which is stream event handling, wherein it's constantly listening to events that are occurring on the streams, and then doing a simple fire and forget. So they're all commonly interacting with the orchestration layer, which would then know how to process those particular requests. Similarly, we have a RESTful service where you can stage like any n number of endpoints as required, and it would forward the request the same way. In the previous slide, I also talked about like shadow scoring. The reason why it was important is that we run multiple models in production where only some of them are affecting the customer. We wouldn't want to make use of every single version of it to affect a customer, as there are certain compliance and standards where a model can only be affecting the customer only if it is MRO approved. And this is a very important step to us. Let's go back to the previous slide once. For the tasks that we wanted to do asynchronous processing, we just publish those events the moment we receive a request to the stream. And given the fact that we have enabled stream event handling where it's listening to events all the time, the moment it realizes that there's a new event that is happening, and it just receives it and knows that it has to forward it to the orchestrator, and orchestrator basically knows where should that particular event end up, or which particular workflow to assign it to so that it can do its own corresponding job. So in a way, if you're receiving a request on one particular workflow where you just have to separate out the working tasks, where one end of it is like affecting the customers and the other end of it is not, this is one way to just completely separate things out. All right.
So we've talked a lot about these workflows in terms of circles and lines and stuff, so we wanted to show you what that actually looks like. So this is a really simplified version of what these look like in our applications, but pretty much to the left here we have the different routes that we're running, so you can run as many API routes in this application as you want, and each one is associated with a workflow. So for instance, this one is associated with workflow A. You can see workflow A in here. The class path is all of the generic plugins that we're maintaining, and you can run as many models, as many business logic as you want. So we have 2 models running and some sort of DB interaction one as well. And then over to the right are the edges. So this describes the data flow between all of the actors. So this makes it really easy to reason about and understand what's going on in your application, and kind of consolidates all of that into one really easy to understand place. So our obligatory programming joke, futures and promises. So when we're looking forward, we have a bunch of things that we'd like to add. The biggest things we're thinking about right now is looking into plugin state level management, especially through Akka persistence. So if a request fails, we want to know at what point it failed and to be able to restart it from there. So that's something that we're actively exploring now. The next is Akka clustering in Kubernetes. We have some proof of concepts in place for this, but we want to be sure that as we continue to scale out, that we have the right technology to do that. So we're looking at using a combination of Akka clustering with Kubernetes for scale. The gRPC protocol is interesting to us because then we'd be able to pass data between our data science models and our application much faster. So we're exploring looking at that as well. And then the last is probably the most futuristic for us, which is looking at the framework as a platform. How do we deploy microservices in a way that makes it really easy for people to put these business logic units together and to deploy them without having developers be interacting with them, setting up all the infrastructure. So thinking about how to make this much more self-service in the future. And we'd also love to hear your questions, but also if anybody has any experience working with similar things, any ideas of frameworks we should look into, any feedback, we'd definitely love to hear it. Thank you.
That's a great question. So something that we don't, sorry? Okay, so the question was, how does this compare to Airflow? Definitely both of them are like a good way to solve orchestration needs, but one thing that we were facing was, how can we integrate the data science models as required into the application without having an issue, like, we wanted to just remove the barrier of like the languages where we can integrate anything as we wanted. The current way we're doing it is we have like a custom solution for the data science models wherein they can be plugged in and just provided to the application, so it's easily pluggable. One big issue is that even though there are other solutions out there, not everything is fitting into our particular needs. We have a lot of custom solutions on streaming, a lot of custom solutions on how do we want to perform our data science models. We found few issues with using other ones like Airflow, and so we decided to create our own stuff.
And your data science plugins are all written in Scala?
No, they are written in Python. Not most of them. We did have like few of them which were also in Scala, primarily when they were trying to use H2O. So the way they just integrated was like they created like a mojo around it, and it was easily shippable, and it was easy to basically plug it in. But most often in like the primary usage that we saw was that it's written in Python.
Yeah, also you allow multiple runtime executions in parallel, actually like different kinds of runtime, Python and Scala in parallel.
So the question was, are we running multiple runtime executions in parallel? Like if Python, Scala, Java, everything in parallel? So the answer is yes. Let's take an example of this particular. Let's take this particular example where there is a small box around 3 particular plugins, and let's say all these 3 are models. Each one of them could be in. First one could be in Python, the second one could be in Scala, the third one could be in Java, and they can all run in parallel without an issue.
In production, it's not difficult to manage?
The question is, in production, is it not too difficult to manage? There are some standard set of challenges that we do face in terms of how do we want to manage. Every use case is slightly different in terms of how heavy it is. Some use cases require, they're like highly dependent on like just models themselves. The others are not entirely based on models, but they do use a mix of it. Most often what we saw is that we have to take care of the compute power that is assigned to the application if you're spinning up way too many models. And other than that, we usually fully test our frameworks like before taking them to production, and typically we haven't seen much issues at all. Does that answer your question, sir? Yeah. Okay. Okay.
How do you measure drift? Like you said, you collecting metrics, right, about the different models and drift for you guys in this platform, and how do you really, do you take back the model to training, etc.?
So we're not doing model training over here per se. It's only the aftermath of model training, where the model training environment is in the development which the data scientists use. But once they have trained the model, they give us the finalized version, which basically is used for affecting the customers in real time. But at the same time, to your question, what if you have the other versions? What is by drift, I'm assuming that you're asking about any kind of additional overhead that may involve, right?
It's basically how accurate is a model performing over time as the data changes. The model may not perform as effectively. So
absolutely, and yeah. So we have other monitoring in place where there's constant retrofitting in terms of like how are the older models behaving, how are the newer models behaving. And it's precisely why we also run the shadow scoring models, which are not impacting the customers. So the moment we determine that a newer version of the model is much better than the one that is currently running, we just swap it out. And the swap out process again involves redeployment, but the redeployment is kind of painless because we are not really messing around with the code anymore. All we are doing is we're just going back to the configuration file and just saying, hey, instead of using model ABC, just use ABC version 1.1. And that's all. It just knows how to get it, fetch it, and like spin it up.
One of the challenges I get in a little bit different case, but then there are a lot of different models running over time. So how do you know how many you have, how many are still relevant, how many just have completely one time patch or something that runs for 2 years now? How do you know that?
There's two ends to that particular.
How do you keep revisions of them?
Right. So, sorry, the question was, how do we keep track of those models that are running for a long time? What is the maintenance approach to it as such? I think it has like a twofold answer to it. One, if the decisions that we're making in real time is impacting real-time customers, and since we also have like a whole lot of audit around it, we have to be constantly checking and monitoring our production systems. So we always try to keep it up to date so we know what is running. Two, given that we also provide extensive logging and then like enable the use case teams to provision their own monitoring systems to monitor what is happening within the system, they know if everything is running as expected or if something is down, in which case there is some kind of an intervention to bring things back up. And it's also like kind of related to the previous question as to what if your model becomes stale and it's not really applicable anymore. So that is when like there is definitely a human intervention which says, okay, this model is not as performant anymore, or like a certain model version is not working anymore. So we basically try to intervene and like figure out either we have to swap it out, or if something is down, like what is a better way to do it. But yeah, it's not completely autonomous. Like the monitoring aspect is still there, where there would be a certain amount of human intervention.
Is this open source, or are plans to open source it?
It's currently in a phase called inner sourced, which is more global to capital one as such. This is a term that we use, where it is not open source to the public, but primarily just within capital one. But there are certain plans, but these have to be properly evaluated as to how we can make it open source. There's a lot of compliance things that we need to go through. So the bottom line is there is no clear date to that as such, but this is something under consideration. And for anyone who may have like visited the Netflix session today, you may have seen like few similarities among Metaflow and this, and I was surprised to see the same talk like a few years ago. Any other questions? Cool, thank you all.